Okay, so I want to start working on indexed rendering. Here's the basic idea. Let's say, well, the classic idea is if we have a rectangle that we want to draw, in traditional rendering we just draw the three vertices, 0, 1, 2, but then how do we draw the other triangle? Well, we would make copies of those same vertices at the same positions and with exactly the same attributes. So we then have, I don't know, 3, 4, 5. So as you can see, some of these vertices get doubled up on, which is pretty pointless. So what we can do instead is we'll have a set of vertices which contain a whole bunch of data, and then we'll have a set of indices which refer to those. So I'll call this point index number 0, and that refers to the first position of the vertex buffer. And then we'll have index number 1 and index number 2, and those will be referring to these things in the vertex buffer. And then I'll have index number 3. Then I need to state which order I'm going to draw these, fetch these points, and I'll do it like this. I'll go 0, 1, 2, and then 2, 3, 0. Doesn't seem like a massive saving, but in the long term, as we add more and more vertices for larger models, we save on space. Now, that reconstruction does get done on the GPU, but it is more efficient than grabbing a whole chunk of wasted data. And there is another benefit to that, and that is later on when we look at ray tracing acceleration structures really like index drawing. So this is all well and good. What I would do is if I went to draw this, I would say something like, okay, so we'll say start index is equal to 0, index count is equal to 6. That's how we would draw that. But then things get a little more complicated, because what I want to do is not just have a whole bunch of different index buffers, but have a big lump where I grab everything all together. So let me go to a more complicated example. Let's say that we have a rectangle and a triangle, and each of them have their own index and vertex lists locally. So I'll call this index 0, 1, 2, 3. Really doesn't matter which order I draw this. And here we have locally index 0, 1, 2. Okay, so I'll consume the rectangle first. So I'll say, okay, the start index is 0. Index count is 4, because there are 4 things. Well, see, this is where things get a little more complicated, because let me draw this up. So I consume this data, and my indices will be going 0, 1, 2, 0, 1, 2, and then 2, 3, 0. So although we do get 4 indices when we go to draw this, we've really got 6. And I messed that up because that's the data that we would have available to us when we go to consume this. Okay, but let's look at the next triangle. So what I'm going to do is I'm going to take all these positions and these indices and append them onto the list that I've got right now. So what I would do is I would look and I would say, okay, how many indices have already been defined? Well, it's easy enough to calculate that we have had 4 indices defined. So if we go, vertices I mean, we go look at vertices, we'll have some data for vertex 0, 1, 2, and 3. So we have 4 vertices so far, and we can check the size, the number of those, and I'll just do like a little local relabel. So I'll say, okay, now this is index 4, this is index 5, and this is index 6. But then, what is the start index? It's tempting to say that the start index is 4, because that's the first thing that I've got here. But if I look at my indices, because this is what I use to draw, when I say draw starting at index 0, drawing 6 things, it's starting from position 0, reading the first 6 things within my index buffer. Okay, so start index. Well, if we go 0, 1, 2, 3, 4, we're going to start actually drawing some of the data which was defined in the rectangle before, which is really not good and really confusing and hard to debug. So what we do instead is we take the number of indices which have been defined so far, and that's the start index for the next shape. So again, I'll pop this data on. So we have 4, 5, and 6. And then index count, it's clear to see from the local index data, which has been defined, that we have 3 indices. This is a very simple shape. The number of indices is the same as the number of shapes. So again, if I were to draw this, I would start at position 6 within my index buffer. So I go 0, 1, 2, 3, 4, 5, 6. So I'm completely free of the previous shape. And then I take the next 3 indices. And of course, well, now the first one is going thing 4. So 0, 1, 2, 3, 4. That's the new triangle position. And that's sort of how we do it. So this has been an overview of what what indexed rendering is, and how we might want to take a number of shapes and compress them together into larger lumps of data. Okay. So this has actually been so useful. I'm actually going to clip this and I'll put this in my fundamentals playlist, but I've also got a Vulkan thing to do, so I'll see you in one of those. Okay, so let's get into the code section here. So here we are at the last project. We have this vertex data, and I'm actually going to redo this. So I'll just pop this in. With a triangle, we're going to have the same number of vertices, but as you can see here, I've just labeled them. And we can create a set of indices down below. So yeah, as you can see, we are drawing the triangle with indices 0, 1, and 2. That's referring to this data up here, 7 floats per vertex. So now we can send this index data along to the vertex menagerie, and that will consume it. And don't worry about the errors. We'll edit this in a second. So now we have a look at the vertices, and these are all two-dimensional, so I'll just pick them by the xy. If we look at these first two, we'll call this position 0, and then position 1, position 2. These numbers are all different, but then when we get back to this one, it's actually position 2 repeated again. And then this one is actually position 0 repeated again. So we have 2 duplicated vertices. So let's change that. Now here, I've labeled them. The 2 duplicated vertices are gone, and everything is unique. So then we also need to specify the indices that we would use to draw this. So as you can see, we take position 0, 1, 2 for the first triangle, and then position 2, 3, 0 for the second triangle, and that is referencing into this array. So then, just the same as before, we'll pass this over to our vertex menagerie, and it's a magical black box for the moment. It's just doing its thing. Now we have a look at the star vertices, and there's quite a lot. So I'll just bring this over, and hopefully you can appreciate that on large meshes, we can save quite a lot of space. Then I'll just bring in the indices. So there we have it. So again, I'll just start talking about how this works. At this point, by the time we get to making this square, three vertices have already been defined. So I would be expecting an offset of 3 to be added to each of these index numbers when they come in. Down at the star, we have 1, 2, 3, 4, 5, 6, 7 vertices already defined. So I would be expecting an offset of 7 to be added to all of these numbers. All right, so let's shift over to the vertex menagerie. So I'll just go model, vertex. I'll do the header first because there are some new things. So just looking through here, we have the constructor, the destructor, that's fine. Now let's look at this consume function. So we're going to take a type of mesh and we'll have a vector of floats. And I'm also going to take a vector of integers, but I'm going to specify that it's unsigned 32-bit. Okay, now finalizing, that's fine, that'll go the same way. But now I don't just have a vertex buffer, I'll have an index buffer. And I'm just going to make these names a little more meaningful, so I'm going to rename this to first indices, and I'm going to rename this one to index counts. There we have it. Alrighty, so instead of offset, I'm just going to change this to index offset. But the rest of this, okay, so yeah, we'll have lump, and this will be a vertex lump. We still need to save all of the vertex data as we're getting it. And we'll do the same thing with the indices. So this will be an index lump. Okay, cool. Let's head over to the source file. And again, I'll just take this top to bottom. So I guess I'll change this to index offset. And by the way, this isn't the canonical way to do this. There's many different ways. As a matter of fact, there's probably a nicer way to do this, but this works just fine. All right, so I'll just set this function up as I had it before. Well, when I say there's a nicer way to do this, it's not that much nicer. It's just a different way. Anyway, I'm getting in my own head about this. All right, so I'm going to change these orders. I'm actually going to take all the appending stuff and throw it right down the bottom. So I'm going to declare this up front. So I want to know a bit of information. I want to know the number of vertices which are coming in. That's vertex count. I'm also going to want to know the number of indices which are coming in. That's index count. And that will be based on the index data. And something else I'm going to want to have is the position. What was it? The last index. So just as I was saying in the diagram section, I don't just want to track the offset, because I actually want the position, not the index number, not the number of the first index, but the actual position within the index buffer where I'm going to start drawing from in the next time. So when I add another shape, that has to be the number of things in my index lump, because it has to be clear of all the data which is in there already. Okay, so where was I? I'm going to take the first indices. I'm going to make a pair. So I'm going to say for this mesh type, I want you to start from this last index. That's your drawing position. And then index counts. And that will literally just be the index count. It's the number of indices that I want to draw. Okay, so fair enough, we'll take the attributes, so we'll append those to the vertex lump. And then what I want to do is take take everything in the incoming index data and append, come on, index lump, there we go. Append not just the index, whoops, but the index plus the index offset. So that's making sure that the indices aren't always just going 0, 1, 2. They are offsetting according to how many have been added so far. So then I'll increment the index offset by the current vertex count. Now, like I said, there is another way to do this. And the other way to do this is, instead of counting up the index offset each time, we could simply take the number of vertices which we have stored so far, maybe up here before we add new ones, and divide by 7. But it's the same thing. It's fine. So that is looking okay. We can close that down, minimize it. And now we'll have a look at finalizing everything. So this is going to go in steps. The first step is we'll make a staging buffer for vertices. So this will be size of float times vertex lump. Okay, and this is all fine. None of this has to change. I'm just documenting it a little better. And then we'll fill it with vertex data. Okay, so we'll take the vertex lump data. Alrighty, then unmap it and everything, and then we will make the vertex buffer, and then fill it, and then destroy the staging buffer. Okay, cool. So in order to do the index buffer, we'll just do exactly the same thing again. I'm seeing double. Okay, so we do not need to redeclare the data type. That's fine. The logical and physical device do not need to change. However, the size does. So I want to take the index lump size, and that is, or a float and a uint32 do have the same size, but let's just future-proof ourselves. Okay, so usage. Now I do have to reset this usage and memory properties, and the reason for that is that this same index chunk was also used to recreate the vertex buffer. So it's tempting to say, hey, last time I made a staging buffer, I had these settings up here. They haven't changed. Well, yes, they have. They've changed here when we made the vertex buffer. So it's just important to be aware of that. The staging buffer actually does not need to be redeclared. We already have one. It was just destroyed. Make a new one. Okay. Then we'll fill it with, just give me 1 second. Indices. Okay, then we'll fill it with index data. Staging buffer is, yep. Okay, that is fine. Then we copy the index lump, and then we unmap that memory. Okay, now we'll make the index buffer. So again, it's all of this, but I'm going to use it as an index buffer. And it will be device local memory. And then we'll create the index buffer over there. And we're just going through the same steps. So we'll fill it up. So we'll fill up the index buffer with the staging buffer, which has been filled, and then destroy the staging buffer. Okay, no worries. So then down in the destructor, we'll do the same stuff, but we'll just do it to the index buffer. So destroy the buffer, free the memory. Okay, awesome. So now our vertex menagerie should be correctly grabbing all that data and preparing it for an indexed draw. Just double check, go back to the engine. no errors. Well, there is an error. I'll get to that in a second. But let me just close this down. Prepare frame, we don't need that. Prepare scene, this, oh, yeah, let's get to this. So, all right, so what we're doing right now is we are binding the vertex buffers. That's good. Let's also bind an index buffer. Okay, so what do we take? Well, we take the buffer. So we'll do that. We'll grab the meshes, index buffer, underlying buffer object. Okay. And then we need the index type. So we'll go Vulkan, index type, and this will be unsigned integer 32. And then, oh, before the index type, we need the offset. So no offsets, we're just using a single index buffer. Oh, what's this complaining about? Ah, that should be dot. Okay, cool. So now both the vertex and index buffers are bound and ready to go. I'll just have to go down to this render objects. And what I want, I'll just rename all of this. So we'll have index count, and we'll grab meshes, index counts, grab that, and then first index, and then the same thing. So we'll go first indices, grab that. So we're using the correct material, and then we go to draw. But what we'll do is we'll draw indexed. So then the arguments there are the index count, and then the instance count, and then the first index. And then, if I remember correctly, let's double check. Okay, first index, vertex offset, and then first instance. Okay, so no worries, the vertex offset will be 0. Okay, so fingers crossed, let's give that a go. If it works, we'll see exactly the same thing as before. Oh, okay, what have we got? Memory location read, oh yeah, no, that's fine. Hey, there's always one of these. So that is, if I go down to the second right, I have actually tried to redefine this, even though it will have the same type each time. Okay, fine, fine. There's always one of those in there somewhere. There we go. Okay, so now we're drawing exactly the same stuff, but we have the self-smug satisfaction of knowing that we are saving space, and as our models get bigger and bigger, we'll be saving even more space. It asymptotically approaches 50% space saving, and then later on, when we do ray tracing, we'll have it set up so that we can construct acceleration structures. But anyway, that was all I wanted to do today. So yeah, thanks for hanging, and I'll see you again soon. Bye.